Okay, so we ended the last video carrying out our significance test visually using the sampling distribution. Let's do so now with a formula. So step 3 in the hypothesis testing model is to carry out the test. So here are two equivalent formula for the large sample test of the mean. So let's look at the second formula. Basically, to compute our value of z, in other words, to determine how many standard deviations our result is above or below the value stated in the null, what we're going to need to do is take our study sample result, subtract from that the value stated in the null, and divide by our estimate of the standard deviation of the sampling distribution. So we had earlier calculated our estimate of the standard deviation of the sampling distribution, and that was 2. Our study sample mean is 105. We subtract the value stated in the null, so our z computes to 2.5. And I'm using this approximately equal sign here, predominantly because we're dividing by a very good estimate of the standard deviation of the sampling distribution, but nevertheless by an estimate. So this just tells us that this z is a very good estimate. Now then, we need to introduce the term obtained statistic, and the obtained statistic is indeed the value that you calculate using a significance tests formula. So in our example, our obtained statistic, and we'll call it an obtained z, is 2.5. I need to introduce the notion of decision rules. So significance tests have decision rules, and these are criteria by which the decision is made to fail to reject or reject the null. The decision rules for a test vary by whether the test is one or two-tailed, and also by the significance level that is used. Another term is critical value. So these are the values of the obtained statistic that guide you in determining whether to accept or reject the null. So here is the decision rule for a two-tailed large sample test of x bar at the 0.05 level. We're going to fail to reject, which is to say accept the null, if the absolute value of the obtained z is less than 1.96, and we're going to reject the null if that absolute value is greater than or equal to 1.96. The final step in the hypothesis testing model is making a decision with respect to the null, or more broadly to the hypothesis pair. So we have indeed already calculated our obtained z. It's 2.5. The absolute value of our obtained z is 2.5, and that is indeed greater than 1.96. Using our decision rule, our decision therefore is to reject the null and accept the alternative. And we can interpret this rejection of the null really in two different ways again of saying the same thing. So one interpretation would be, given a true null, the probability of obtaining our particular study sample result, x bar equals 105, or an even more extreme result, that probability is less than 0.05. Or a second interpretation, the probability of obtaining the study sample result, or an even more extreme result due to chance alone, is less than 0.05. In this example, we can indeed be 95% confident that the null is false. And we've rejected the null here. I mean, rejecting of the null and statistical significance go hand in hand, so our result is indeed statistically significant, and we could be more explicit and we could say it is statistically significant at the 0.05 level using a two-tailed test. And again, we used a two-tailed test because our hypothesis pair is non-directional. Let's go ahead and stay with our same example, but let's presume that rather than using a significance level of 0.05, that we are using the 0.01 level. And we will continue to presume that our hypothesis pair is non-directional, and therefore a two-tailed test is in order. As presented in the last video, at the 0.01 level for a two-tailed test, the rejection regions are the upper and lower 0.5% tails. So compared to the rejection regions for the 0.05 level, these tails are smaller and further from the value, in other words, that they begin further from the value stated in the null. So when we use a 0.01 level, it's going to be more difficult to reject the null. Indeed, we're going to need to be 95% confident that the null is false if we're going to reject at the 0.05 level. We'll stick to the formula for now. So we have a distinct decision rule for the large sample test two-tailed 0.01 level. And here is that rule. We're going to fail to reject the null if the absolute value of the obtained z is less than 2.58, and otherwise we will reject the null. So, I mean, our calculations are done. I mean, their calculations are, we did that in the last video, and our z, actually we did it in the beginning of this video, and our z calculated to 2.5. Here are our vertical bars symbolizing absolute value. The absolute value of 2.5 is indeed 2.5. 2.5 is less than 2.58. So our decision following the decision rule just presented here for the 0.01 level is to fail to reject the null. So we're going to accept the null, and we are going to reject the alternative. So here's a visual look at our sampling distribution and results. So the 5% tails on each side are the rejection regions, and these tails begin 2.58 standard deviations from the mean. So this, as a quick calculation, our estimate of the standard deviation of the sampling distribution is 2. 2 times 2.58 equals 5.16. So the rejection region at the upper tail starts just a little bit above 105 at 105.16, and then over here the rejection region begins just a little bit below 95. We plot the location of our study sample mean. It is not in the rejection region. It's very close to being in the rejection region, but it just misses being in that region. And so we're failing to reject the null. So this figure then is basically carrying out the significance test visually, and we get the same result doing it visually by seeing the result is not in the rejection region as we did by using the formula. I mean, the formula made use of the critical values. At the 0.01 level, two-tailed test, then our decision is to fail to reject the null. So here's a comparison of the rejection regions when we use the 0.05 level and when we use the 0.01 level, and you see that the rejection regions when the 0.05 level is used are larger and that they begin closer to 100, that is, to the value stated in the null. So here our result is indeed in a rejection region, so we reject at the 0.05 level, and here it just misses being in the rejection region. The rejection region begins right there. So it is indeed more difficult to reject at the 0.01 level than at the 0.05 level, other things being equal. Well, in some sense, the researcher wants to reject the null. I mean, that's the decision that, in essence, there's a real difference, So in this example, that those in your parenting intervention have better skills than in the large national sample that provided the value for the norm. So the question comes, why would one want to use the 0.01 level rather than the 0.05? So let's answer that question by introducing the notion of type 1 error, which is oftentimes symbolized by alpha, and indeed the risk of type 1 error is always equal to alpha. Type 1 error is the error of rejecting a null that is true. Now, given a true null, the risk of type 1 error equals alpha, or stated differently, it equals the probability connected with your significance level. So if you have selected the 0.05 level, then the risk of type 1 error is 0.05. And if you have selected the 0.01 level, your risk of type 1 error is 0.01, 1 time in 100. Now, suppose that a researcher selects the 0.05 level, and suppose that the researcher conducts 100 significance tests. I mean, in essence, draws 100 random samples and carries out the appropriate test for each of them. Now, suppose that the null is true in each case. I mean, I guess we could call this a thought experiment from the perspective that in real world you'd have no way to know whether the null was true or false, but we'd presume that for our little experiment here, the null is always true. So, what's the best guess of the number of times that the researcher will reject the null? Well, when you use the 0.05 level, 5% of means are in the rejection regions. In any given sample, there is a 5% chance of, by the luck of the draw, obtaining a mean in the rejection region. So your best guess on any given pick is that there's a 5% chance of picking a result that will end up rejecting the null. So if the researcher carries out 100 different tests, your best guess is that she'll reject the null 5 times. Now, recall that in our example, we've defined the null to be true. So she will make about 5 type 1 errors. She will about 5 times reject a null that is in actuality true. So use of the 0.01 level reduces the risk of type 1 error. It reduces the risk of rejecting a null that is in actuality true. It reduces that risk from 0.05 to 0.01. So when you select the 0.01 level, and then let's say that you indeed do reject the null, you can have 99% confidence that the null is false. In essence, you can have 99% confidence that you haven't made a type 1 error. So basically that's a good thing. When you reject at the 0.01 level, you have increased confidence that the null is indeed false, and increased confidence that your decision to reject is indeed the correct one. And in some situations, just 99%, well, 99% confidence is always better than 95% confidence. It's tricky to know what is the level of confidence that should be required, and this is where 95% confidence is sort of by tradition the standard that researchers most often use. Now, on the other hand, though use of the 0.01 level reduces risk of type 1 error, it increases the risk of type 2 error. Type 2 error is the failure to reject a false null. So there's a bit of tension, in essence, between type 1 and type 2 error. In essence, as the probability of one goes up, the probability of the other goes down, which is basically to say, if you use the 0.05 level, you are increasing your risk of type 1 error, but reducing that of type 2, and vice versa. If you use the 0.01 level, you're reducing your risk of type 1 error, but increasing that of type 2. So in hypothesis testing, the decision making is, it's probabilistic in the sense that the researcher never knows assuredly whether her decision is the correct one. She'll never know assuredly because she'll never have data on the full population. Here is a scenario that presents the true state of affairs in the population and then the decision that the researcher makes. And so there are 4 quadrants. Now, when the null is true, sometimes the researcher makes a type 1 error, and indeed, probability of that error equals alpha. So we know the probability of type 1 error. It's simply 0.05 or 0.01, depending on which significance level is used. Now the probability, here's the sort of, so to speak, the opposite error. A false null in reality, but the decision being to fail to reject that null. So that's an incorrect decision. That's a type 2 error. The risk of type 2 error is higher at the 0.01 level than at the 0.05 level. Now we are not going to, in this text, learn fully how to compute the probability of type 1, of type 2 error. But so what you really kind of need to know for now is it's in tension with type 1 error. And I think you want to have a picture of these 4 quadrants. That when the null is true, and indeed the researcher makes the correct decision 95% of the time at the 0.05 level, and an error 5% of the time. And we can't be quite as precise in the situation when the null is false. This shows the probabilistic nature of decision making with respect to the hypothesis pair. You never know assuredly whether your decision is the correct one.